Okay, guys, lecture number 9 for the radiation physics course here at Nashville General Hospital out of the Carlson, Adler, and Ballack book. Um, Diving into chapter 4 today. I think we started with chapter 4 with electrostatics, and now we're into electromagnetism and induction, which are probably one of the two big breakthroughs that got us to practical use of electricity out of. So when Ben Franklin was researching and Augusta de Coulomb and all the others and electrostatics and Leyden jars and such, there wasn't a whole lot of practicality to it. It was more just, well, you can do these parlor tricks. When you host a party, you can get yourself a little bit of amber, solid amber, and some wool, and you can create some static electricity, and you can you can zap people, and you can show electrostatic repulsion and attraction and things like that. But nothing as far as improving the quality of life. Well, with the exception of the lightning rod, nothing really improving the quality of life. Not like we know electricity today. So these two ideas, electromagnetism, that is, electric currents can affect magnetic fields and create magnetic fields, and then induction, changing magnetic fields, can create electric currents. Those two ideas, especially that second idea, um, gave us part of, or at least in part of the Industrial Revolution that swept through England and all of Europe, and then later America. Okay? And so now we're blessed to live in the post-industrial age where we have artificial light sources, we have electricity, and we just kind of take it for granted, but it wasn't always the case. So let's look into these ideas and see how we get closer and closer to electricity and electrodynamics, which is going to be our next lecture. Okay, so we're going to start with understanding magnetism. We understood electrostatics. We explored electrostatics, and basically it showed us how electrons behave. Protons too, but they don't really move. So we talk about the electrons, and we covered that. Now we're going to talk about magnetism and magnetic fields, magnetic attraction, and repulsion, and you're going to find a lot of similarities between the behavior of magnetic fields and the behavior of the electron, and what that the fundamental truth is that Mr. Faraday, Mr. Oersted, Mr. Maxwell all kind of got to the conclusion is, I think it was Faraday that first proposed the idea, is electricity and magnetism are basically the same thing. They manifest in different ways, but they are the root causes of both electrostatic force and magnetic force come from the same location, and that is charged particles. Okay, and so we'll talk about magnetism and how we get magnetism to show up on the human size scale, because it is a atomic property. It is a property of either a proton or an electron. Typically, it's got to be a charged particle, but all charged particles exhibit magnetic fields. Now, from the scale of electrons and protons, then we have atoms and molecules, and then substances and compounds and things. So as you add complexity, it's sometimes the case that you cancel out the magnetic fields, and that's how you get non-magnetic materials, is at some stage in the game all the magnetic forces are brought to balance, or they are randomized and inflexible in their randomization, and then you would get non-magnetic stuff, so to speak, matter. Okay, but other times something very, very special happens, and it happens with iron. And iron is great because it is ferromagnetic, and so it shows us this stuff. Iron might be among the most useful materials that we've ever discovered. Um, but iron exhibits magnetism down on the atomic level, and then that scales up to the lattice, the molecules, I guess. Um, and it can scale up to an entire macro-sized object that we would call a permanent magnet. So we'll walk through the classification of materials. We'll walk through the atomic nature of magnetism. Now, a lot of that I'm just going to hand off to a video by Minute Physics, coupled with Derek from Veritasium. And the video is embedded here, so my students seeing the lecture live will watch that video. I encourage you to go it will be on the Minute Physics channel. Just go and seek that out, and that's the best explanation of magnetism I've ever seen. So we'll talk about Fleming's rules for electromagnets that come in very, very handy when we're trying to understand the transformer later on. We will get to the transformer when we talk about circuit devices and the X-ray circuit. The X-ray circuit relies on about 3 transformers, the basic X-ray circuit does. And Fleming's rules and Faraday's law are embedded in the proper function of a transformer. And so we'll talk a little bit now. Fleming's rules for electromagnets apply to solenoids and electromagnets, but they also apply to transformers. You just have to make one simple adjustment. So I'm not sure if I'll cover the simple adjustment for transformers today, though. That'll be for a later lecture, but we will reflect back to Fleming's rules when we talk about transformers and Faraday's law of induction, both of which will be covered in this lecture. Okay. So we're going to talk about electromagnetism and electromagnetic induction. So what is the fundamental difference? Electromagnetism is you use electricity to create a magnetic field. Typically, you're talking about a static magnetic field, that is a non-moving magnetic field. Okay, but occasionally you want a changing magnetic field because that's how you get induction. And so electricity can create a magnetic field. That magnetic field, if it fluctuates, can create more electricity. Okay, and that is how our power plant generators work, is that electromagnetic induction, where we're using magnets to push current, okay? Or changing magnetic fields to push current. So several factors that regulate the strength of electromagnetic induction. We'll talk about the 4 factors to optimize current production with electromagnetic induction. And then briefly touch on the principle of self-induction. That is going to be important to us in the X-ray machine schematic. Self-induction is exactly what it sounds like. If we have electricity creating magnetism, that creates electricity in the same circuit where the electricity, so the cause and the effect are manifest in the same circuit. So you get an electric current creates a magnetic field. If that magnetic field changes, it creates electric current in the wires that created it. So it's a self-fulfilling prophecy type situation. Self-induction sounds strange, but there's nothing that says it can't happen, so it does happen. It's one of those type of things. All right, so magnetism is a fundamental force, right? It is related to electricity in that the root cause, again, is a charged particle. Okay. Typically, where we get a magnetic effect, though, is the charged particle is moving, either linearly or curved if it's being accelerated through space, or it possesses a spin, which means, see, the theoretical physicists don't like to say it's actually spinning because they don't like to admit that the electron's a particle anymore. But we're here over second cousins of physicists, our X-ray scientists, are perfectly happy for the electron to maintain a particle identity. And so, yeah, spin means spin. It means what a top does. So, what a gyroscope does. And so spin to us does mean spin, and therefore it's moving, therefore it has a magnetic field. So anytime a charged particle, electrons typically, but also protons and positrons, they will exhibit a magnetic field when they're moving, and they could be moving velocity ways or they could be spinning. Okay? And so that's the difference between the orbital magnetic moment, which is effectively the electron moving through space, versus the spin magnetic moment. Even if the electron is not moving through space, like in an orbit, it still possesses spin. Okay? And spin is easily understood if the electron's still a particle, and that's why, but the physicists balk at that, and so they have a difficult time defining what spin is, because spin is an action of a particle. You can't, if it's not a piece of matter, then how is it spinning? Okay? How is a wave spinning? And so that's where the definition, the classical definition of the word spin and what you think it means, that's why if you go and you seek out other theoretical physicists on the internet for explanation, they'll kind of like, they'll say it's not a conventional spin. The electron's not actually spinning. Well, they say that because that would mean that the electron's a particle, and they've already determined that it exhibits wave-particle duality as well. But we're ignoring that part. Okay? It's a particle, it spins, and it moves through space. Both of these create magnetic fields. Okay? The orbital magnetic field is shown in the illustration here. And so there's magnetic field lines, kind of like a shock wave, or like the exhaust of a rocket. You can think of that. It is similar to the magnetic field disturbance of an electron passing through. So. Now that magnetic field disturbance, the orbital magnetic moment, this cylinder-shaped magnetic field that is most concentrated right at the point where the electron is, and then starts losing energy or losing field strength as the electron passes by and gets further and further away. That will come in handy when we're trying to figure out Bremsstrahlung. So keep this picture in mind. When Bremsstrahlung comes up, remember about the orbital magnetic moment of the electron. Okay, so magnetic dipoles. Magnetic dipoles are magnetic fields. Every magnetic field has two poles, a north pole and a south pole. Okay, and so even the electron, when it possesses a spin, the spin is north pole up or north pole down, or north pole left or north pole right. However you want to draw your electron, that's fine with me. As long as you recognize that it does have a magnetic moment, and therefore it has a magnetic field, and when we draw a magnetic field, we typically just have an arrow pointing to the direction of north. And so the electron spin has a magnetic north. If it's got a magnetic north, it has to have a magnetic south. Okay, that's the whole concept of dipoles. There are no monopoles. So you know how you can have an electron and it's a negative charge? And you could say, well, where is the positive charge? Well, protons carry a positive charge, but we don't necessarily have to have a proton to have an electron. But the same is not true for north and south poles. If you have a north pole of a magnetic, you do have a south pole. It's somewhere. Just because you haven't found it yet doesn't mean it doesn't exist. Okay? And the mathematics solves for, now whose mathematics is that? Well, Gauss, and then later the calculus version, Maxwell, and I think I scared the crap out of you with that when we talked about electromagnetic waves. You saw those four equations that looked like, I don't know what, they look strange. That's calculus symbols. The second rule said no magnetic monopoles. It said there is no source to the magnetic field. So you have a north pole and a south pole, but if you look at that location, there is no particle there that is giving you the north pole. There is no particle that yields a south pole. Okay? So it doesn't have the same complement as the electric field, where there is a negative pole that's called the electron. There is a positive pole that's called the proton. Okay, there is no north pole particle, there is no south pole particle. When one of them appears, the other one is there somewhere in the field. Okay? Now, domains. Each electron has a magnetic field. Each proton, and therefore nucleus, has a magnetic field. A lot of these magnetic fields cancel, but there are certain elements like iron that have unpaired valence electrons, and their unpaired valence electrons have spins that are the same, so that the north pole of both of those electrons are pointing the same direction. And that makes the atom, the iron atom, magnetic. And so the sum of the valence electron magnetic moments becomes the magnetic field for the atom. But a lot of times these cancel out, especially if you have a full valence shell, it cancels because there's 8 pairs of spin up, spin down electrons paired up. And that's how electrons pair up, is one spin up, one spin down, or opposite magnetic dipoles. And so there's a lot of canceling of magnetic fields. But occasionally, like in iron, there are matching magnetic fields, and so the entire atom takes on the magnetic field of the matching unpaired electrons in the outer shell. And that's why iron is magnetic. Okay. Now, you can also have atoms that are magnetic, and there is video on this, and I think it's the next slide. But those atoms arrange themselves so that the magnetic fields are not pointing all in the same direction. So that makes the material non-magnetic. While iron can actually flip its atoms to align in domains, which are regions of atoms or molecules in a material where all the magnetic fields are pointing the same way. The domain, and that creates a domain. If you align enough domains within, like an iron bar, all the domains align and the entire bar exhibits a single magnetic field. We would call that a permanent magnet. Okay? All right. Now, what does a magnetic field look like? Well, it looks like a torus. What the hell is a torus? It's a donut. Okay, it looks like a donut. So if you draw a donut, you've drawn a magnetic field. Okay, The top of the donut hole, so lay a donut, down like you usually do on the plate. The top of the hole is magnetic north. That's where all the flux lines are coming out of. And then they wrap back around the surface of the donut and they enter in magnetic south. And now inside the donut hole, the magnetic field lines go from south to north. Outside the donut, the magnetic field lines go from north to south on the outside of the field. All magnetic field lines are closed loops, creating a donut shape, or a torus, as the physicists like to call it, a torus shape, because that's the shape in advanced geometry that you get that's donut shaped. Okay. And so these lines of force, they're called lines of flux, and the field strength increases where these lines bunch up. And so that would be at the north and the south poles of the donut. Okay. The SI unit for field strength is the Weber. Okay. And the field strength divided by the surface area is the magnetic flux. We will not be working with that equation. Okay. All you need to know is the real key is as the field lines bunch up, the magnetic field increases in strength at that location. That will come in handy later. All right, so this is the video. Not going to play it during the recorded lecture. Yeah, go and watch that on YouTube. That's on Under Minute Physics and what are magnets, basically. So, and so magnetism is really the stacking of atoms. So atoms exhibit magnetic fields, for one, because they have unpaired valence electrons. And if all those atoms, all the atoms in a particular area of a material have their magnetic fields pointing in the same direction, well, that's a magnetic domain. If you combine all the domains into a single domain throughout the entire object, like an iron bar, you get a magnet. That is, all of the amplitudes of the individual magnetic fields create larger magnetic fields. Okay, so these lines of force never intersect. They form a donut shape. Now you might not see the donut shape here because this is a two-dimensional rendering of the donut shape. You have to imagine the top loop coming out of the page like a slinky and curling around and connecting to the bottom loop. And then you'll see a half donut. And then do that again going into your screen from the bottom loop and curling back around and connecting to the top loop. And now you can see the donut. Okay. And so every magnetic field has this torus shape. And again, there's a North Pole end and a South Pole end. Okay. Those are conventions, just like we have plus and minus signs for charges. Okay. It's something we made up so that we can better understand this, so we can give it some kind of structural integrity and some kind of pattern that repeats. So there's a North Pole and a South Pole to a magnetic field, and every magnetic field is a donut shape. Okay, our flux density, which is just Weber's, which is magnetic field strength, divided by area, meters squared, length times width. It's measured in Tesla and Gauss. Okay. Earth's magnetic field is 1 Gauss, okay, which is 1/10,000th of a Tesla. Our modern MRI machine are about 3 Tesla. Okay. So very, very strong. Probably that looks like, is that 30,000 times stronger than the Earth's magnetic field? That's pretty crazy. Yeah. Okay. So here we have your classic iron filings experiment, Woolly Willy. Um, Go to Cracker Barrel if you don't know what Woolly Willy is. Okay. It was a kid's toy back from my days. I fondly remember Woolly Willy. It was iron filings trapped under a plastic clamshell, and then there was an illustration of a man's face, and that was Willy. And you could take a magnet wand and pull the iron filings onto Willy's face and give him a beard, and thus he was Woolly Willy. Okay. But what I didn't know at the time is those iron filings were actually tracing the magnetic field for the little iron wand, the little magnetic wand that you used that you got with the Woolly Willy kit. Okay. All right. So there are natural magnets, artificial permanent magnets, and electromagnets. Okay, those are, practically speaking, those are the 3 types of magnets. There's also superconducting, but those are a subset of electromagnets. We'll learn about those next fall in MRI. So natural magnets, that's lodestone, which is a special type of iron ore. Lodestone forms when liquid molten iron from the mantle gets to cool slowly. When it gets to cool slowly, the iron atoms that are in a liquid state get to align with the magnetic field. So you have this volcano, shoots out a chunk of iron rock, liquid, and that lands in the middle of a pasture or whatever. Okay, and it cools slowly. While it's semi-liquid still, all the iron atoms align to the Earth's magnetic field, and therefore they align to each other. So we have this liquid rock, this lava, cooling slowly, allowing time for iron atoms all to align with each other because they're in the liquid state. And then when it does finally cool, that rock is magnetic. That's lodestone. Okay. And that's exactly how it forms. If iron is heated up to a liquid but cools too fast, the individual domains of the iron atoms don't get a chance to sort themselves. And then you don't really get natural magnet lodestone from that. There are other iron ores that are not magnetic at all, but lodestone happens to be magnetic. Okay. Now, as far as industrial engineering, we figured out that aluminum, nickel, and cobalt mixed together in an alloy. It's a combination of metals. In the right concentrations and mixture forms a fairly strong magnetic domain. And so these are your refrigerator magnets and other types of magnetic devices that you might use. You can find these. Oh, alnico magnets are used in push button controls like on video games and x-ray control panels. And then coming along in my lifetime was the neodymium magnets, which are a rare earth metal that also can be cooled slowly such that they form a permanent magnetic field, stronger than lodestone. Neodymium magnets are perhaps, I don't think we've created a permanent magnet engineered a permanent magnet stronger than a neodymium magnet at this time. Um, as far as a solid chunk of metal that exhibits a magnetic field, the neodymium magnets, I have some here, and I can show you, but I've already gotten 2 blood blisters from them, so they are very powerful. And then our most powerful magnets that we've been able to engineer are called electromagnets, and they use electromagnetic induction to create a magnetic field. Okay? But like the slide says, electromagnets only work when you turn the power on. So you have to have moving electricity in order for the electromagnet to exhibit a magnetic field. Well, that's curious, isn't it? Hang on just a second, if you would. How is it doing that you just push current through this object and it makes a magnetic field? It's got something to do with the electrons. Yes, in fact it does, because we know atomic magnetism by the video originates with the electrons, and so there must be something to moving electrons around in a certain way that creates a magnetic field. Okay? Well, this looks familiar. This looks like the first rule of electrostatics. Like charges repel, like poles repel. And so if you line up 2 magnets, north to north, south to south, those magnetic fields will repel each other. The closer you get them, the greater the force of repulsion. Well, that sounds familiar too. That sounds like Coulomb's law, but for magnetic fields. Yes, we would call that Gauss's law for magnetic fields instead of Coulomb's. It looks exactly the same as Coulomb's law, except for instead of the sum of the product of the charges, you put the strengths of the magnetic fields in the numerator. Okay. But inversely proportional to the square of the distance from the source holds true because it's a field. So it's got a field effect. There's a distance component involved. All right. Now, most of the time, the repulsion is not the useful part, except for when you want to make a friction-free train. Then, yeah, if you want to do like a high-speed locomotive, you would, to eliminate friction, you could hover that locomotive on repulsive magnetic fields. We have toyed with this idea for about 20 years. I'm not sure if Japan has a hover train or not, but that's pretty cool. Levitating a whole train by electromagnetic repulsion. Totally a thing that could be done if you have a strong enough magnet. All right, so letter B is what we're typically used to in the practical application of magnets. When you align a north pole to a south pole, that is opposite poles, the magnetic fields attract each other, and you get a little click and they stick together. Okay, and depending upon how strong the magnetic fields are, determines whether or not you can get those things pulled apart. See the neodymium magnets and the blood blister that I just mentioned. All right. Hey, this is Gauss's law. The force between 2 magnetic fields is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. That sounds exactly like Coulomb's law, but we're not talking about electric field force or electrostatic force. We're talking about magnetic force. And we're not talking about the product of the charges. We're talking about the magnitudes of the magnetic fields. Yeah. And there's a constant and there's a distance. The 4 pi r squared is the distance. So, yeah, sounds very, very familiar. Sounds just like a reiteration of Coulomb's law for magnetic fields. And that's exactly what it is. And so this is a key piece of evidence that several people working with electricity and magnetism thought that they were the same thing. I believe Faraday was the first one to definitively hypothesize that. All right. So magnets demonstrate polarity. That is, there's always poles involved. There's a north pole and a south pole. Magnetic fields always exist as a dipole. Sorry, Sheldon. If you're a fan of Big Bang Theory, you understand that that's the research paper that he was working on, was to try to isolate a magnetic monopole. Well, if you watch the video, you can see that you can break up a magnet and you create two magnets, and then you break up those magnets and now you have four. And you can keep going down all the way to the atomic level, and even a single iron atom has a north pole and a south pole. So no magnetic monopoles. That would require a source particle, and there is no source particle. All right, so magnetic induction. How would we make a magnet? Well, you're going to take an iron bar. In the picture at the top, picture A, a regular old iron bar that's not been magnetized has random domains. That is, clusters of atoms that have unified domains, unified magnetic fields, but several domains pointing in several random directions cancels out the magnetism of the entire bar. Okay? And so, yes, it's vector addition, very much like acceleration in the opposite direction from the velocity is a negative number. If you have arrows pointing oppositely, they cancel each other. And so the sum of the magnetic fields becomes zero, and you don't have a magnetic field. But if somehow you could convince all the domains to align in the same direction, well, then you create a magnet. The iron bar becomes magnetized, if you will. This is the essence of electromagnetism, and this is how we make permanent magnets to this day. Is you take a chunk of a material that is known to have ferromagnetic properties, and then you just submit it to a very strong magnetic field, and over time all the domains align within the material and it exhibits a magnetic field because all of its domains are aligned. All right, so various materials have two general characteristics, okay? And the relationship is inverse. Permeability, the ability of a material to become magnetized, and retentivity, the ability of a material to hold on to its magnetic properties. Okay? And so if you have a material that has high permeability, then it will have low retentivity. That means you can magnetize a piece of iron, but it's not likely to stay that way. Okay? And so either domains are adjustable and atoms are adjustable, or they're not. And so if they're adjustable, they can take on magnetic fields and align to external magnetic fields. But they can also lose that alignment once that external motivation is removed. Okay? Now, things that don't readily become magnetized, it's because the atoms and the domains refuse and resist alignment into a unified magnetic field. Okay? But they are very stubborn in holding on to the magnetic field that they're exhibiting now. But unfortunately, those are random orientations and they all cancel each other. So ferromagnetic things can become magnetic or exhibit magnetic properties. They have high permeability, low retentivity. Paramagnetic or non-magnetic things cannot become magnetic, and they resist changes to the orientations of their domains and their individual atoms. Okay? And so magnetic, paramagnetic, diamagnetic repels all magnetic fields, and then non-magnetic cannot be magnetized. Non-magnetic materials also happen to be electrical insulators. So glass is non-magnetic, plastic is non-magnetic, rubber is non-magnetic. Okay? I need to look up and see what is a diamagnetic material that repels all magnetic fields. That's just wild. Okay. All right, give me just 1 second. All right, so electromagnetism. Ørsted, just before Faraday, took a little pocket compass. He was playing around with electric circuits. He had a simple circuit with some conductive wire in a loop, a switch, and a battery. And he might have had a light bulb on here, or a resistor, or a motor, something to offer resistance. And then he put a compass in various locations close to the wire. And what he found is when he flipped the switch and started conducting electricity, the compass needle changed direction and pointed straight at the wire. Okay? And so he repeated this experiment a couple of times, moved the compass around, moved the compass closer to the wire, farther away from the wire, and the wire was exhibiting all the properties of a permanent magnet when the power was on. As soon as the power is off, the compass goes back to pointing at magnetic north of the Earth's magnetic field, like compasses do. Okay. And so, yeah, basically, electric currents can create magnetic fields is his discovery. That's Oester's discovery. Electric currents create magnetic fields. And so you need charges in motion. You need these electrons to be in motion, because as soon as I open the switch or remove the battery, as soon as I interrupt the conditions for electricity, then I also no longer have a magnetic field that is affecting the compass. So this is a very simple experiment that you can perform yourself. Even I'm not sure why I haven't built a model of it yet. Maybe I'll be motivated to do so this year. So, all right. And so Fleming came along and said, well, there's certain rules for the magnetic field that's created. So he took Oester's experiment and he kind of figured out how the magnetic field was oriented relative to the wire. Okay? And he did this by common frame of reference. That is, he used his fingers and his thumbs to indicate the direction of the magnetic field, the current, so on and so forth. The path, the direction of the conductor. And so he came up with a list of rules where you can hold your hand in certain positions and it's going to mimic certain parts, either the direction of the magnetic field, the direction of current in the wire, or the direction that the wire is moving, or the direction the magnetic field is moving. And you flex your fingers in a certain orientation. There's pictures in the book. We're going to memorize a couple of these, especially for the solenoid, because that's going to come in handy for us when we talk about the transformer. Okay. So if we're, so the first one, the right hand thumb rule, if we hold a solid conductor in our right hand and our thumb points in the direction of Franklin current, Mr. Shepard, then the magnetic field lines coil around the wire in the direction of your fingers. Okay? And so it gives you a circular magnetic field around a straight wire. So if it gives you a circular magnetic field around a straight wire, what does coiling the wire in loops do? It's a very good question. Okay. The left-hand thumb rule indicates the turning of a wire rotor in an electric motor. So with your left hand, you point your second digit forward like you're making finger guns with your thumb up, and then you take your third digit and you extend it 90 degrees from the palm of your hand. And so the wire, if the field is pointing forward and the current is flowing from left to right, then the wire will go upwards. Okay. It's very easy to see that as the direction of the field changes, the motion of the wire changes, and so you can get a rotational motion out of this if you keep applying that field and that current. You'll get the motion indicated, but that will start looping in a circle. And that's very handy if you want rotational motion. This is the principle under which motors operate. So this is going on inside your vacuum cleaner. And I do have a motor demo, and I'll show you that, how that spins. And you can actually see the sparks shoot across the commutator when we run that. It's an old vacuum cleaner motor. All right. The right-hand thumb rule applied to the solenoid. All right. So a solenoid is a coil or a helix of wire carrying an electric current. Works for electromagnets and transformers. In the transformer, we have to remember that the current is constantly changing direction. It's AC. And so that means we have to keep flipping our hand, right thumb up, thumb down, so on and so forth. So again, take your right hand, and now this time with your fingers, trace the path of the Franklin current. You have two options. The Franklin current, opposite the electron flow, can be going clockwise through the coil or counterclockwise through the coil. For a DC current, it's only going to be flowing in one direction. And so your thumb will point the direction of magnetic north when you curl your fingers in the direction of the Franklin current. So in this diagram, it looks like the current's flowing counterclockwise. So take your right hand, curl your fingers counterclockwise, and you'll see that magnetic north is up. Well, how would you curl your fingers counterclockwise? You would have to flip your hand over, invert your hand, curl your fingers the other way. Now magnetic north is pointing down because your thumb is pointing down. And so of all the Fleming's rules, this is the one that helps the most with understanding the X-ray circuit. Because we do deal with coils of wire, and it's helpful to figure out the direction of the magnetic field as current is flowing through the coil. Now transformers, that current is constantly changing direction, so you're typically taking a curled fist hand with your thumb sticking up and then flipping it over and then flipping it back and then flipping it over and then flipping it back. And that's what's happening in a transformer. And I'll tell you the importance of that when we get to transformers. All right, electromagnetic induction. I thought we already talked. No, we talked about electromagnetism. Currents can make magnetic fields. Induction is the opposite principle. Can we move a magnet past a conductor and therefore change the magnetic field around a conductor to create electricity, that is, flowing current? And so Michael Faraday read Oester's paper, probably completed his experiment to see it was reproducible, and then just started thinking, and he just come up with a brilliant opposite. What if is the opposite true? That is, what if I start with a magnetic field and expose a coil of wire to a magnetic field? Would that create electricity? And lo and behold, it does. And this is the way we generate electricity primarily today, is moving magnets past coils of wire. Okay? Now you need a relative motion. You can totally move the wire past the magnetic field. You can move the magnets past the wire. As long as they're moving relative to each other, then Faraday's law works. So you have some generators where a coil of wire spins in a magnetic field. You have other generators where it's the magnetic fields that are spinning on a wheel, alternating north-south electromagnets pointing outwards, and the coil of wire is around the outside of the wheel. That's how a hydroelectric generator works. Okay? And so it's important to remember a changing magnetic field will produce an electric current, like we see at the red arrow. That is a turning wheel meant to spin a conductor past a permanent magnet. That is a device called a dynamo. It was first invented by Faraday, and I don't think Faraday held the patent though. I think there were several people that developed dynamos at about the same time, and so there were competing dynamos. But Faraday certainly was one of those people that said this can be used to generate. Here's a little hand crank on this wheel. I think his had a copper wheel that ran through a horseshoe magnet, and then he had brushes, one at the axle and then one at the edge of the copper, and the brushes made contact with the wheel, and the wheel, because it was going through a changing magnetic field, created an electric current inside of it. So this picture here shows two gentlemen. They look to be brothers. They have some kind of apparatus on the lab workbench. Looks like the one brother that's sitting down is holding a stopwatch. And there is a dynamo generator there. Do you know what kind of apparatus this is? I hope you do. This is an X-ray machine, ladies and gentlemen. This is in fact a picture of the first X-ray ever taken in the United States of America. The poor boy getting his wrist radiographed is being attended to by the physician that's standing over him. And that bright white light that you see hovering over his wrist is actually the inside of the X-ray tube, the glass X-ray tube, the Crookes tube. That's his mother sitting behind him. He fell and slipped on the ice. And they went to see the physician, the standing man, who had a brother that was a physics professor at, I think it was Dartmouth College. And this is actually the X-ray machine built by the physics professor brother in the Dartmouth College labs at the physics department at Dartmouth College. So, yeah, don't tell us we're not physicists. We're totally physicists. The first X-ray machine was operated by a university physics professor at Dartmouth College. We're totally physicists. Okay. Unified theory of electromagnetism, those big scary calculus equations. Let's go through them one more time. Electric fields are created by charges. Electrons and protons create the electric field just by being present. Okay. There are no magnetic monopoles. Moving electric charges create magnetic fields. Changes in the magnetic field will produce changes in the electric field, and then changes in the electric field will produce changes in the magnetic field. Okay? Therefore, if we create a repeating wave in the electric field, we will also create a repeating wave in the magnetic field. We already explored that idea. That is the photon, ladies and gentlemen. There's those scary equations one more time. Okay. And so, great, practical use. We can create electric current with just moving a conductor through a magnetic field. And so how would you build such an apparatus? Well, what you're wanting to build is called a Faraday dynamo, and this is what I described 2 slides ago. So a brush is a wire brush. It's got conductive, the brush hairs are actually fine little pieces of metal wire, okay? Because charge concentrates at the sharpest radius of curvature, fine pieces of metal wire will pick up loose electrons if they're being pushed or pulled in a certain direction. And so as you spin this copper disc through the horseshoe magnet, north pole on one side of the disc, south pole on the other side of the disc, as the disc rotates, it experiences a changing magnetic field. And so the copper disc starts pushing the electrons either toward the edge or toward the axle. I'm not sure which, but it does start pushing the electrons. Okay? And when it does this, extra electrons enter the brush connected to the axle. Let's say they go through the meter, it shows a current, it comes out the other end of the meter, and then those electrons deposit on the edge of the copper disc where they are pushed again to the central axis. Okay? And so it forms a closed loop. We're moving electrons around. That's electricity. Okay? So how do you build a bigger, better dynamo? Well, you need a strong magnetic field. So the stronger your magnets, the more current you're going to be able to produce. The speed of the motion between lines of force, that is, the velocity of the flux relative to the conductor. Okay? And so the faster you turn the hand crank, the faster the copper wheel spins, the more force is going to be exhibited on those electrons in the copper disc. And so they're going to be motivated to accelerate. And so that will increase your current, moving the magnetic field faster relative to the conductor. The angle between the lines of flux and the conductor should be 90 degrees. And so if you have a wire and a length of wire, the magnetic field should be cutting through the transverse plane. That is, the north pole should be running 90 degrees, and then the south pole 90 degrees as it spins around. Okay? And so if the magnetic field and the run of the conductor are oriented 90 degrees to each other, then you get maximum amount of current produced. So if your magnetic field is off angle from 90 degrees, you're not going to get as much current. Okay? And then the number of turns of the conductor. For Faraday's copper wheel, it would be the mass of the copper wheel or the volume of the copper wheel. Okay? For our modern generators, it's going to be the number of coils of wire we expose to a changing magnetic field, because that's how we do everything now, is coils of wire. Now, Lenz followed on the heels of Mr. Faraday. Lenz was a Russian, while Mr. Faraday was British. Okay. Um, but these two countries were allies against Napoleon, and so they might have even communicated. I don't know about that. But Lenz definitely read Faraday's work. He read Faraday's paper, might have even visited London and attended a couple of Faraday's lectures. Okay. Um, Lenz observed that the current induced creates an oppositional magnetic field to the original magnetic field. And so this is Faraday's law is typically called the Faraday's Lenz law because Lenz's phenomenon always shows up. That is, you get an opposing magnetic field um, in the induced current opposing the original magnetic field. And so, yeah, these generators kind of stick to each other because oppositely aligned magnetic fields are attracted to each other. And so you need a rigid framework for your electric generator. It's got to be a big, heavy object so that the wheel doesn't stick to the wires, so to speak. So Lenz's law shows up in MRI. It is, yeah, it's a big factor. And of course, this opposite magnetic field can induce currents, which can create magnetic fields, which can induce currents. And it's basically an endless cycle of currents. That's where eddy currents come from, which are like little whirlpools of current and whirlpools of magnetic field. And so the thing becomes complex. Becomes kind of like a fractal diagram of magnetic fields. Little tiny interfering magnetic fields that are little whirlpools, the eddy currents. So, yeah, Lenz is always assumed to be part of Faraday's law. But we give credit to Faraday didn't actually discover this part about the oppositional magnetic fields. Okay, so that's it. That's magnetism in a nutshell, and that is induction and electromagnetism. Okay, so magnetism is a atomic property. It's chemistry. It's a property of some of the elements of the periodic table. But not all of the elements. And just because a material is magnetic at the atomic level doesn't mean that translates up to magnetism at the macro level, at the human perspective level. And so domains, atoms have to form domains, and then all the domains have to align, and then you get a magnetic field observable at the human scale. Okay? We went through the shape of the magnetic field, the rules regarding magnetic fields, very similar. We saw the similarities between magnetic field rules and electrostatic rules. We talked about north and south poles. We talked about Fleming's rules. Fleming's rules for the solenoid and the electromagnet is probably going to be the one we're going to wear out the most. That's also called the right-hand rule. And so I showed you that with a coil of wire, you get a magnetic field. If the current doesn't change direction, you get a static magnetic field. That is a permanent magnetic field, and that's if you stick an iron bar in the middle of that, that's a electromagnet. Okay. We talked about electromagnetic induction, which is kind of the opposite. So electric currents create magnets or magnetic fields. Moving magnetic fields can create electric currents. That's induction. That's Michael Faraday. Okay. We talked about how to maximize this effect so you get the maximum amount of current. There were 4 principles to that. Strong magnet, high velocity of motion of the flux relative to the conductor, more coils of wire in the conductor, and then a 90-degree orientation of the direction of the magnetic force lines versus the run of the conductor. So the length of the wire has got to be 90 degrees to the direction of the magnetic field lines. And that's all we have for electricity, electromagnetism. Well, not electricity, electromagnetism, magnetism, and electromagnetic induction. We're going to tackle in Lecture 9 electrodynamics. We're finally ready for electricity.